Hi guys, and welcome to today's lecture. Today is October 13th, and we are in week 9. And today also is an important day for you guys for your lunar observation. I was actually kind of nervous, honestly, when I saw the weather yesterday, and I thought that maybe we're going to have a problem today because they're expecting inclement weather tomorrow, or at least rain or clouds. But it looks like it cleared everything. I'm looking at the window in here, and there is not a single, at least from my angle in here, not a single cloud in the sky. It looks like the project is still an ongoing project, so that you guys should not lose your observation today. I know yesterday probably if you tried, you might have had some difficulty, and if you try tomorrow, you might have some. So actually today is your day, which is really the scheduled day anyway. So hopefully you guys will take care of that and complete your project in time too, okay? So that's one thing. The other thing also today is the last basically unit from the solar system. We're going to be moving to a new topic, as a matter of fact, today. And we should be able to make progress toward where we're supposed to be going. I know I made a big fuss last time about the exam and the fact that it has to be moved and so on and so forth. So most likely the exam is, as I said before, is going to be moved to the proper place for it, okay? So this is in terms of where we are on things. And let me share with you the screen. There was a question in the chat and basically the answer to it. For those taking the lab, of course, you're not all required to do it. Nobody's required actually, but some of you opted to do it. So yes, we have a lab today and it's going to cover the calculation basically of the mass of Jupiter. And we hope to finish it all today. I know we have about 3 hours or 3 hours, yeah, together. We should be able to do the whole thing today, okay? So let me share with you guys let me close something in here. I just noticed that something is open and namely Photoshop. I don't need Photoshop, it slows down the computer. If it closes, yeah, no, I don't want to save nothing. No. Okay, so now let me get into my units, and it's unit 49. Here it is. So unit 49 deals with the comets, and this is the last topic basically from the solar system. Basically what we did was we looked at the Earth as a planet, we looked at the moon, we looked at Venus very closely, all of these 3 objects very closely. We looked at both Saturn and Jupiter. We looked at the moons in general for all of these planets, including that of the Earth in comparison. We looked at the ice worlds, we looked at the dwarf planets, we looked at the we didn't really go in depth into the asteroid belt and the Kuiper belt, and those are probably, some of them are coming right now. Maybe we're going to discuss them, especially in terms of the comets. And the last thing are the comets, because the comets are played a major role in the history of the solar system and continue to do so, because they are the ones who bring lighter materials to inner planets. For example, for the case of the Earth and even that of the other planets, they bring water, they bring different kind of elements to the planets. So and it's a common, it's actually something that you see in the sky too. So we really need to understand them. So we're going to describe the features, the time sequence, because they have a period through which they have to go through, and also the origins where they emanate from. Basically, at this point, most of the comets are coming either from the Kuiper belt, and those are the short-lived comets. Basically, they have a small period. They only a few basically years or so, and then you have the long-term comets that take a long time to come back to the Earth, to pass through the Earth, to go through the sun and go back. And those, they must come from further away than the Kuiper belt, and they come from the Oort cloud instead. So the Oort cloud was the hypothesis, and based on this observation itself concerning the comets. So and we're discovering stuff in it right now. So that's basically their origins. And then we're going to talk about meteor showers, because as these comets heat up as they approach the sun, They develop, of course, a tail, they develop a comma, they develop all kinds of materials that they start to basically shed because it's heating up and it's evaporating as they pass through. So they leave in their wake a gas, okay, which is essentially those small particles and small dust that they leave behind, which is mainly water, actually, for the most part, but they still have other minerals and stuff like that. So as the Earth goes, and any other object goes through them, because for the Earth it has a big atmosphere, so they goes through the leftover of that material the comet passes by, that stuff starts to fall on the Earth. But because the Earth has an atmosphere, those as they gain speed falling toward the Earth, they heat up. And for the most part, they evaporate, but they leave a trail, okay? So those are the meteor showers that you see on a specific times. One of them is actually going to happen not tomorrow. Tomorrow is the 14th. A week from tomorrow is going to be our first shower, okay, meteor shower. And then they have, not our first, I mean, we have been having them, but at least since we started talking about them, this is the biggest, one of the biggest ones, and there will be several of them throughout the year, okay? So what you do in this case is, the way you measure them is tell me how many meteorites you're going to have in 1 hour, okay? That will show you the intensity of the meteorites. So that's basically what we're going to be talking about in this last unit of here. So this is one of the pictures in here. This is the McNaught comet. And notice that it has really two things going on for it, okay? It has a more or less a line curve that is going along with the path of it. And then you have a long curve that is curving around. Depending on the type of particles, if they are charged, they're going to be influenced by the magnetic field of the Earth. Because charges interact with the magnetic field in a sense that they spiral in it, okay? Whereas in-charged particles, neutral particles, they're not impacted by the magnetic field at all. They're impacted by the radiation pressure coming from the sun. Remember, the sun emits light in all frequencies, and that's the next topic, as a matter of fact. And that creates a pressure, just like the wind creates a pressure on the sail for the people going on in the oceans in the old days. I mean, now too. So that is sailing in the oceans using those big, basically the big structures. So now the wind pushes them, and the boats move in the ocean. This is not exactly similar. Let me tell you why. Because a particle of the wind has a mass. It's a particle, actually. It's particles of the wind. So it's really dust and also water and whatever is in the wind that is being blown away against the boat, okay? The sail of the boat. So in this case, it's going to push it, physically push it. It's like you take your hand and you push against something. Whereas radiation from the sun is not made out of particles. It's made out of light. It's made out of energy, really. But it exerts a similar pressure on the dust, on the particles in this case. So it really is a pressure, but not coming from material pushing against another material, but rather it's an energy. Okay, so this is something that that is basically that forms. Obviously, the comet, as it's far away from the sun, it's too cold to develop even a comma, let alone the dust that is going to evaporate from it. But as it gets closer from the sun, as it passes Jupiter, basically, and approaches Mars, at least in that region where the two move, then they start to evaporate. They start to heat up, and that's where the comet develops, and that's also where the material starts to evaporate, and that's where the tail actually starts to form. So this is basically, in a nutshell, what a comet is. So a comet, I mean, a comet has this huge structure, okay? So the comet structure, part of it, which is really the heart of it, extends about 100,000 kilometers. That's a lot. 10 million kilometers. That's all. I mean, if you take the Earth to the moon, if the Earth is on one side, the moon is about 3 times the size of the comet. However, this extension of the hydrogen in here the gas that is basically leaving. The reason why it's hydrogen, not anything else, is because it's a lighter material. It's the lightest gas there is. It's the lightest material there is. So now, because the comet doesn't really have much gravity to hold on to materials, so the lighter ones are going to be basically further away from it. So the hydrogen expands to about 10 million kilometers, about 3 times the distance from the Earth to the moon. So if you put the Earth in here, the moon is somewhere in here, plus the moon in here, plus the moon in here. It's about 3 times that distance. Slightly less than 3 times, but that's basically the extent with which. So it's a huge structure. That's why we see it. Otherwise, the comet itself, if it's too far away, it's a very tiny rock. I mean, it's a very small object. Over time, this process, basically what it does in this case is going to evaporate the comet, and over time, comets basically dissipate. They don't stay forever, okay? So, and the inside is where the nucleus is. It's about 10 kilometers on average, okay? 10 kilometers is nothing. It's less than probably what, it's about 6 miles, basically. It's like a small city, okay? Like Redlands or something like that, okay? So these are some of the comets that we have in here. The most famous of one of them all is at least the one that is gained fame with the scientists is Halley's Comet, Wild 2, Temple, and some of these comets basically they have been actually visited. We sent actually probes to them to study them and see and so on and so forth. Okay. Halley's Comet has a history on how it was discovered, in a sense that after Mr. Kepler published his work, and then Mr. Newton explained his work using his laws of motion and also the law of universal gravity. It was Halley actually who noted this comet. I mean, people noted it before too, but he made a prediction. He made a bold prediction based on the calculations that he learned from the mechanics from Newton, that he's going to come back in about 76 years from today, he said. Sure enough, 76 years, within a day or two from his predictions, the comet returned again. So this is amazing. This is a triumph for science. This is a triumph for Newton, actually, for his work there too, okay? Just to show you that science, in order to make it valid, you have to make predictions, and these predictions should be testable predictions. So he made the prediction, and he said that, okay, 76 from me today, this comet is going to come back. Can we test this? Absolutely, yes. We'll wait 76 years from today and see if you were right or wrong. And sure enough, it was correct. So that means the model is correct up to that point, okay? So, so how comet becomes visible? Basically, at this point in here, it approaches it's really an icy surface when it's far away, but then the ice, which is mainly water and even carbon dioxide and other materials, they start to convert back into sublimate, in this case, into a gas, and that is what you see. That how the tail forms with that dust that comes out of the evaporation process because of the heating. Okay, there are two features in here. There is an ion tail. This is basically the charged part of it. This is directly pointing away from the sun. So if the sun is here, this is perpendicular to that circle that where the comet is around the sun, centered around the sun. And there is a reason for it, because the radiation from the sun, namely the magnetic field from the sun, basically should be helping this particle to move away from it, okay? So this is a charged, that's why the ion in this case, and it's a blue because of the radiation that is emitted in this case, because of the transitions in this case in the energy. And there is a dust tail. This is in charged particles. This is really following the law of gravity. When you take a rock and you throw it, it curves a little. So that is basically the difference between the two tails. Okay. Studying this will tell you a lot about its structure, what it's made up of. So again, as the comet approaches about 4 to 6 astronomical units, remember Jupiter is 5 astronomical units. So around that point in here, as it's approaching, I should say, from this side, it starts to heat up and starts to develop, starts to diffuse a little. around 3 astronomical units, which is a little further than Mars before Jupiter. I mean, on this side of Jupiter. Then the tail starts to develop the two kinds of tails. Now you have an ion tail and you have a dust tail. And both of them, they're pointing away. They are pointing away from the sun. And as it turns, they are still pointing away from the sun. So at one point, they're pointing toward where they came from. But then at the end in here, they are pointing toward the other direction, the opposite direction, until they turn. And the radiation from the sun and the solar wind, which is actually charged particles, also will push this radiation in the opposite direction. And then the tail starts to basically fade until it reaches, again, starts to freeze after you pass around Jupiter. That is where the frost line is, and that is basically where the comet is. So it's going to be a solid rock again, basically, of frozen material at the end, and going to stay for a long, long time. I remember Kepler's law, the third law, that the distance, in this case, squared, and it should be the second law in this case. Equal areas are swept in equal amounts of time. So if I take this area in this case, in 1 week, for example, or 1 month or 3 months, it's going to be the same area as this from here to here in 3 months. But because the radius is small, the curve must be a lot bigger than the curve in here because the radius is bigger. So that is the second law of Kepler, actually. That deals with the areas, which means that it's moving faster around the sun. So it comes very slow and then gains speed and then slow down again. So most of its time really is spending it away from the sun. For the most part, comets are away from the sun. When they reach the sun, they go fast and then they go back into to far reaches because of their highly eccentric paths. They still obey Kepler's laws, all of them. They're not just the second law. So again, they're rich in carbon dioxide, as I mentioned, monoxide, methane, ammonia, and water, of course. They're the ones that bring a lot of water. And measuring its density will tell you exactly what it's made up of. They're the ones that brought water to the surface of the Earth and even all of the other planets. Because remember, as the Earth formed, it was so hot that most of the materials in here, like the water, for example, dissociated and broken down into all of the other components. So that water would not have survived if they existed at all. So the water that the Earth has came later on through comets, okay? So again, the hypothesis is this: they must be coming from very, very far away, distances that are almost incredible in this case. So the Kuiper belt in here, which extends anywhere about 50 astronomical units, that is a flat disk, similar to where the planets are, namely the ecliptic, okay? But then at far away distance, those are a lot lighter materials, and those are materials that were thrown away in all of the directions, and now they're spread all around. So there is a sphere that sets them, that is centered around the sun, where all of the materials are. This is where most of the long lived comets are. They come from that region. Now in 2017, I think October, I forgot the exact date, 2017, this object that seemed to have come to Earth in here, let me check the date in here because this is a big deal in here, okay? Because there is more debate now on it too. So when was that exactly? October, I believe, October 19th. Okay, October 19th of the year 2017. There was a comet actually that was, I believe, initially people thought it was a comet. Here is a problem with this thing here, okay? First of all, it did not really have a comet tail, and it was moving too fast. As a matter of fact, so fast that it could not have been coming from the Oort cloud still. If it was in the Oort cloud, it could not have gained enough kinetic energy to be moving that fast. As a matter of fact, it was not discovered until it was too late. It already has passed the Earth, passed very far away. So that really opened up, and so guys, you can Google it, and there is a debate actually in the community. There is a small number of scientists who believe that's actually not a comet altogether. It was not an asteroid altogether. First of all, it's an extraterrestrial object. It's an extrasolar object. It came from outside of the sun completely. This came from another star, and the minority believe that actually some sort of an artifact from a different civilization, from extraterrestrials, basically, some sort of either part of a probe or something else to come and basically examine the solar system, because it was moving too fast, number one, to be from the solar system. And then it has this weird shape that is some sort of, it looks like a cigar, actually more like a space, basically some sort of a capsule. And then also, some people think that according to the numbers that they have seen, that seem to have accelerated actually. In other words, it was not powered by the force of gravity. So Mwamwa for you guys, but for the vast majority of scientists, they basically believe that no, it's just a rock that came in, and it's shaped as such because of its interactions with a lot of materials on its way here. So that's in 2017, October 19, 2017. You know, one of you guys heard about it? Oumuamua? No? Yes? Maybe? It doesn't matter. If you'd never heard of it, you heard of it today. So it's a good thing to go and look at it, because if it turns out to be really an alien vessel of some sort, then at least we know that we really have been visited, at least in 2017. This was the first object that was actually, we know that came from outside of the solar system. There was another one that came, actually another one, but that's really confirmed a natural object. It's not an extra, it's not a civilization made, if you wish. We can say man-made, because if it's made by people who are not men, at least not from this earth. Anyway, so these are some of the stuff that has to do with the meteors. And right now there is a brand new, basically, field of astronomy where people are hunting for this extra solar system objects. Okay, so again, the meteor showers are this leftover from the comets. Okay, so whatever is left, all of that dust and particles that is left, remember that as it evaporates, it's going to leave in its wake all of these things. So as the Earth is moving around the sun, it's going to encounter some of them. But for us, they appear to be coming from a special, from that constellation where they're coming. For example, if you're looking in here and you look at the sky, they appear to be coming from this constellation or from this constellation. So it was a puzzle in the old days, but now we know what they are, okay? So they're named after the constellation where they appear to be coming from. But they're actually in our atmosphere. They're not actually coming from any star or anything like that. They're actually, the Earth is hitting them, and it's hitting them in that from the upper atmosphere. Okay. Again, so when you look at them, they look at coming to you like this. When you look at them from the night, they fall as if they're falling on the Earth, and that's why we call them meteor showers or meteorites. The effect is similar to if any of you have ridden or drove in the snow. You will see if the snow is light, not too heavy snow, of course. If the snow is light and you're driving fast enough, the snow, instead of falling down, which is really what's going on, it's falling down, it appears as if it's coming to you, to the windshield. If you look and you're driving, the snow, the different pieces of snow appear to be flying toward your windshield. And that is because of the effect that you're driving through the snow. This is similar to that effect. The meteorites themselves are standing still, actually, and the Earth is going through them, and it's moving with tremendous speed, 30 kilometers per second, much faster than you can even drive. So they appear to be coming into you like the snow is coming into when you're driving. So that's basically what they are. And they're given names depending on the constellation that they are coming from. Perseids, Leonids, and the Leonids are coming from Leo. That's a constellation where they appear to be coming from. And this is basically what I was talking about in the beginning, namely October 21st are the Orionids, and they're coming. They appear to be coming from Orion. So if you go on that night, which is not Saturday, not Saturday. I mean, not tomorrow, not this Friday, but the Friday next, which is the 21st of the. If conditions are ripe, and most of the time conditions are good here in Southern California, try to go outside and enjoy the show. This is Halley's Comet, actually. This is what was left over Halley's Comet when it passed last time. It was in the 1980s. It will not show back until sometime in the toward the end of the 20th this century. Okay, so 21st century. So toward the end of the 21st century, we are in the 21st century already. Anyway, so it appears coming from Orion. Okay, and it's not really intense. It's 15 to 20 meteor per hour. Okay, that's a maximum we're going to have. I mean, you go in an hour, it's 20, so it's about probably every, what, 3 minutes there is one? So every 3 minutes there is a meteor. That's why it's a shower. It really is a beautiful show, okay? When you do that, please try to go to I mean, I know hills in here in near Redlands and Colton and Loma Linda, the hills there, they're actually a beautiful place to go and look at it, okay? There is a place where you can go and sit there. I don't know, probably the site too, next to the pass, the Cajon Pass. Maybe you can find the place where you can go and enjoy yourself. If not, you can just go outside in your backyard and enjoy the show. November 17th is the next one. That's a Lineates, and they're actually not that many, relatively speaking. And then you have December 14th and December 22nd. Those are 1 week apart. There is the Geminids and the Ursids. Geminids are coming from the Gemini, and Ursids are from the Ursa Minor. So that's basically how you're going to see it. And this is actually similar or slightly less in intensity than the ones that are coming next Friday. The ones I usually look forward, honestly, are this one in mid-December, because there are a lot, okay? So almost every minute there is one, okay? So it's really an intense event. So that's the December 14th in near Gemini constellation. You have a chance, go there, go outside of the town completely and enjoy it, okay? So these are some of the ideas behind this chapter, behind this unit, I should say. Let me introduce the next unit. Any questions so far before I move on? No? Okay. So let's move on. You see, now we went all the way to 49, we're driving back to, to 21, because now we need to build some stuff before going back into the 50s to continue or resume. So we're going to do 21, 23, 2, 23, 24, and those are due part of the this exam. 25 actually is going to be deferred to the next exam, okay? So there is a reason for that, and you will see it hopefully down the road, okay? So again, we're going to talk about light. Light was a mystery. Light was a puzzle. People wanted to understand light from a long, long time. One of the questions that people wanted to understand is how fast light moves. There was a belief, or at least an argument, for light being traveling instantaneously, because if you take a candle and you light it, and somebody even 10 meters away from it, they will see it immediately. 10 meters is far. It's about what, 30 feet? 30 feet away from you, they will look at the light and they see it immediately. So the belief was that it was moving I mean, it's not super fast. It was really instantaneous. It goes everywhere, wherever it wants to. That argument was basically pushed aside by a lot of people. Among other people was Al-Hazen. He said, look, if it is true that light is moving with an infinite speed, basically, then there should not be any difference between our days and our nights, because those dots in the sky, namely the stars, they are sending light. And if light is traveling with an infinite speed, so they should be coming from all directions so that the day and night will be similar because of that lighting effect, that accumulation that is coming from very far away. So he argued that the speed is finite. So Mr. Galileo actually wanted to measure the speed of light. He measured a lot of things. He measured the force of gravity, basically the gravitational acceleration, and he found it to be 9.8. And he came up with a lot of measurements, and he came up with the concept of speed, basically quantized, and concept of acceleration quantized, and he came up with all interesting stuff. So he wanted to find the speed of light. So what he thought of to do is the following. He and a friend of his decided to go on two different sides of a hill about a mile away, about 1.5 kilometers. And he told him to do the following. They had what do you call them, the not candles, I lost the word. Lighting source, okay? They have lights, let's call it that way, although at that time they use gas, different kind of liquids to light them. So they had them sitting on two different sides of the mountains. So I told him, do the following. When you see the light I light from here, light yours. So now Galileo thought of the following. If I light my light first, and wait for the light to travel all the way to my friend who was sitting about a mile away from me, can't hear me at all, then he's going to light his. Once he lights his, the light will travel from his source up to me in here, and I will see it. All I have to do is measure the time. Since I know the distance is about a mile, but remember, light goes and come back in this case. So he's going to send light to his friend, and his friend send him light back to him. So that's actually 2 miles in a sense. So I take 2 miles divided by the time I measure, and I'm in business, and I know how fast light is traveling. So he was documenting. He didn't have a clock. He didn't have a watch, actually. He didn't have a good way of measuring time. The only thing that he had was his wrist, basically. So he was measuring the pulses on his hand, trying to see how fast light was. And that's for most of his experiment was he was using as a clock, as a watch. So they did this experiment, and he was collecting the time because he knows the distance. All he needed was just the time, and he collected a lot of data. Repeat again, repeat again, repeat again, repeat again. And he had a big table in here of data, a lot of data, in the hope that he will take that distance, which is about 2 miles, divided by the time, and now he has the speed of light. He saw the data going all over the map. So he just told them, you know what, let's do the experiment differently now. You stand next to me so that the distance is nothing really. You stand next to me. Don't light your light first until you see mine. So you have to really look first. Once you see it, light yours. So he did the experiment again and lit his, start measurement. His friend lit his, and then noted the time, noted the time. He found that they're absolutely the same thing. So he took all of his data and threw it in the trash, basically, and said, all I was doing actually is measuring my reaction time and that of my friend, that's all. So the data is useless. So he knew, or he thought at least the speed must be big, but he couldn't find it. It took the work of Romer, actually, later on, to measure how fast light was moving. And for Mr. Romer, what he noted, of course, at at his time, Galileo has already discovered the moons of Jupiter. One of them is Io. He noted that Io, as it goes around Jupiter, takes almost 2 days, 42 hours to go around Jupiter. As it does today, the Earth, let's say, for example, is on this side, and Jupiter is moving back and forth. So it gives me a period. 6 months from today, the Earth will be on the other side of the sun, and it's going to give me a different motion. But light now here travels only between the Earth and Jupiter, which is about 4 astronomical units. On this side, it's about 6 astronomical units. So there is that additional 2 astronomical units, which is about 300 million kilometers where light has to travel through. He can find the difference in time between those 2 events, divide the distance, which is about 300 million kilometers by that time. And now he has found the speed of light. The way he found it was only about 200,000 kilometers per second. So it was off by a big number, by 100,000. But for the first time in history, we have actually a number associated with the speed of light. That is why Mr. Romer is remembered, because he took us I mean, he found the answer within 67%, which is about 33% is a big error, but it's still better than have no idea like the work of Mr. Galileo. Now we have a number to work with. Later on, Mr. Fizeau actually did something else to find the speed of light. He did a gear system where he had gears basically spinning, and then he sends light, a monochromatic light of the same color, sends it through the gears, hitting the reflector and coming back to him. Obviously, if they hit the gear and they come back and they hit it and blocked, so the light is not going to reflect. So he had to adjust the speed fast enough so that the light will go straight through and come back, okay? And from there, he measured how fast this rotation is versus the distance that the light has to travel back and forth, and he found the speed of light to be closer to 300,000 kilometers. The experiment was refined later, and now we know the speed of light, that it is 300,000 kilometers. Light is actually radiation. Light is a vibration of the electric field and the magnetic field, okay? And they travel in all directions. Well, you know electricity is dangerous. I mean, case in point, the plugs behind you are dangerous, okay? And that is not much of a voltage, actually. It's 120 volts, and 120 volts can kill a person easily. But we're talking about electric fields that have intensity much higher than that. I mean, at least the ones coming from the sun on the earth in here. So the question is, why are we not electrocuted? Well, there is something called the polarization. In this case, it's the direction of the electric field, the one in red in this picture. For this particular wave, it's pointing, let's say, for example, up and down. The magnetic field is left and right, and it's traveling in and out. So that is really the behavior of all of the electromagnetic radiation, namely light in general. Well, the direction of the electric field is by definition what the polarization of light is. But this ray happened to have been in this direction. There is another ray next to it where light is completely in an opposite direction. The electric field is in an opposite direction. The magnetic field is in an opposite direction to this magnetic field, and so on and so forth. So the net effect in here is, yes, we are swimming in kind of a sea of electromagnetic radiation, because that's what light is. But at the end, we have no effect. We're not being electrocuted because they all cancel out in terms of when they interact with your skin. But eyes are sensitive enough to detect the different frequencies that they hit it, and different materials that reflect different frequencies. Remember, I'm talking about polarization, but it's still light is coming this way and that way, but it's coming with the same wavelength. The wavelength is this distance from peak to peak. So if I start, for example, for the red, it doesn't matter red or blue in this case, both of them are going to give me the same frequency. So from peak to low to peak again. That is, the distance in space is the wavelength. In time, it's the frequency. So those are two big characteristics of any wave. In the case of light, that's how it's described. Whether you're talking about that of the electric field or the magnetic field, this is the same thing, okay? This is because one of the big works that later on came in is that due to Mr. Maxwell, who unified electricity and magnetism and optics. Optics is the study of light. So he all merged them into this study. So the electric field and the magnetic field are really what causes light. The vibration in this field is what causes light, okay? Because that's where the mystery now answered. So again, it's a small disturbances in electric and magnetic field that travel. By the way, your eyes are more sensitive to the electric field than the magnetic field. That's how the eyes evolve. All of eyes, not just our human eyes. Because the magnetic field is super weak compared to the electric field. It's about 300 million times less than the electric field. That's why it's a waste for the electrons in your retina, which are in the part that is sensitive to light. They respond to the changes in the electric field, and they don't care about the magnetic field, because the magnetic field is 300 million times smaller. So it doesn't matter for it what amount you have. But the electric field now matters. The brighter the light, the more intense the electric field. Your eyes will be, the electrons will be moving basically in and out a lot. But the higher the frequency, meaning toward the blue, the faster they're going to be moving, whether they're going to be moving short distance for low intensity light or a high distance for a high intensity light. So this is, in a sense, basically what light is. So they have a name now. That was Mr. Einstein gave them that name, photons, because they are particles of light. Because light, here is the problem with it. It's a wave. The way it's represented right now, it's a wave. And it is. It is 100% wave. And it's a transverse wave. There is no question. It has a wavelength. It has a frequency. It obeys the law of the so-called dispersion law that relates wavelength and frequency with the speed of light, the 300,000 kilometers per second that I mentioned before. So it's a wave. There is no question about it. But also it's a particle. If you ever owned one of those photocells or even a watch that has the solar charging capabilities, that takes basically light, and light acts as a particle hitting the cell and ejecting an electron off of it. So that's a particle, really. And that phenomenon was explained by Mr. Einstein, and Mr. Einstein won the Nobel Prize for it, for doing that explanation. And he gave them that name of photons. So light, the bottom line is light is a wave and light is a particle. And why that is a big deal? Well, because those two things are not connected whatsoever. As a matter of fact, they're antagonists to one another. A particle is something tangible. It has a mass. It has a physical size. A wave does not really have a physical size. I mean, the waves on the ocean, for example, are those disturbances. Energy is transmitted, but the water itself is really not going in and out. It's just going up and down in the same place. The same thing, the string, for example, if you hold it stretched and you play a tune on it, yes, the tune, you're going to hear it, which is the energy being traveling in the air, and the vibrations, you will see it, but the string itself is in its place. It's not moving from end to end. I mean, it's going back and forth, but this particle in here of the string is not going to go to the end of the other string. No, it's going to stay in its place, whatever it is in the string. So the point in here is particles are not the same as waves. Yet for the case of light, it seems light has these two antagonist ideas exhibiting them in the same time. And this is what is known as the duality wave particle for light. Okay. If you study this subject later on, it turns out this is not unique to light. Even particles like electrons and protons and any particle you can think of also has that duality. So particles also behave like waves and waves behave like particles. That's basically in a nutshell. It doesn't seem to make sense, but that's exactly how nature presents itself to us. We don't have a choice in the matter. We have to take it for its face value. Again, light as it travels, and you experience this one if you have a candle, for example, in the middle of the room and you come close to it, you can read off of it. If you have a light bulb, for example, and you're near it, you can see well. If you leave the light bulb or the candle far away from it, you're going to probably see less of it. You probably cannot be you will not be able to read. And if you travel very, very, very far away from it, you may not even see the candle or see even the light bulb, because light travels over a sphere, not a circle, over a sphere. And as it travels in all directions, it's the same light that originated from the source. But now it's spread over bigger and bigger and bigger and bigger spheres, so it thins as it spreads out, and it thins in an inverse law with the size of the sphere. And the sphere is 4 pi times the diameter, times the radius, squared. And the radius squared in this case is the distance. So light near the sun is more concentrated from wherever you are on a square meter, for example. Light away from the sun is less concentrated, like toward the Earth. If you move toward Mars or Jupiter or even further away, there is less and less concentration because it spreads over bigger and bigger spheres. As far away from the sun as you can get, the sun will appear to be a dot probably because its light basically diminishes even further. If you travel far away from the sun, you probably will not even see the sun because it's going to be just part of the background. Dark background. So that's what's going on in this case. So again, what is light, at least from the particle perspective? Of course, we know, and some of you probably took chemistry or at least heard of this stuff in here before, that the atoms are made up of a nucleus. For example, this is hydrogen, and electrons. For the case of hydrogen, it's only a single electron. And the electron orbits in specific energy levels. Okay. And the ground state, when the atom is not excited, it's going to sit on that specific point forever and ever, spinning basically and going fast and fast around it. And it's a fuzzy structure, but first approximation, let's take it as a dot moving around another dot, which is the center. If you excite the atom, meaning you put it through a voltage or you heat it up or do something to it so that the electron doesn't stay in the ground state and moves up to a higher energy level. What I mean by higher energy level, any higher energy level, whether the second level, the third level, the fourth level, it doesn't matter which level you're talking about. Now the atom is excited. It's not in the ground state anymore. So it needs to get rid of that excess energy. So what it does in this case, the electron drops to the next energy level, or drops 2 energy levels, or drop 3 energy levels, or drop all the way to the ground state in the same time. It's going to either cascade down to the ground state, or it's going to jump straight to the ground state. Okay. The point being in here that you really need to remember is that this is not a physical jump, really. I mean, yes, it is a physical jump because its radius also changes, but it's actually not a smooth transition. It goes from here to here. Okay, disappears in here, appears in the other level, because quantum mechanics, the science that describes it, is kind of weird with our I mean, for us to understand. It's really a real science too, but sometimes it's hard to describe things in our daily experience because what's going on that microscopic level is outside of the scope of our daily experience, let's put it this way. Again, all of the chemical elements exhibit this similar behavior, like hydrogen, and except now you have more and more electrons, and as more and more electrons, more and more energy levels, but it's still usually the outer electrons are the ones that do chemistry. Okay. Okay, you have 2 kinds of spectra, really, and this is laying out the foundation for the next actually units. Okay, when light hits a material, it can be absorbed. So what's going on in here? The electron jumps from one energy level to the other energy level if and only if it's hit by or absorbs the right amount of energy. If the energy is more or less, that transition is not allowed. So the only way that a transition is allowed between a ground state and an upper state, if that frequency and only that frequency for that specific transition can be observed. So in that case, light as it goes through the atoms will go unimpeded for the most part, except those selective ones. For those sitting in Astronomy 125, we already did this experiment, and in the absorption spectrum, there will be missing lines. So all of the lines are going through, except some that are missing. What happened to them? They were absorbed. And they're always going to be absorbed by that element. So it's really the absorption spectrum is a unique signature to that element and that element only. A different one will have specific energy levels that can be absorbed, that can be transitioned to. In which case, the light that is going to go through it can only be absorbed through those values and only those values. So again, that element will have a different signature when it comes to absorption spectrum. This is a very powerful stuff. Because if I were to see a spectrum, an absorption spectrum, and take those lines that are missing, I can compare them to what I know from the other elements in the laboratory. And I can tell you specifically that this material has this element in it, and this element in it, and this element in it, just by virtue of the fact that analyzing those spectra that are missing and tell you exactly what elements makes up that material. That is why this unit is important, because it helps me, even without having to travel all the way to the stars, tell what the stars are made up of. Okay, as opposed to an absorption spectrum, you have the emission spectrum. The emission spectrum is somehow the material is excited, whether through heating, whether through electrical processes, whatever process, collisions, whatever process that gets it excited, or through an absorption of radiation, the material wants to go back to the ground state. Okay, so what it does, it's going to emit and emit only those specific frequencies that are unique to that transition for that material. Again, if I were to see an emission spectrum, For a material, I could unambiguously tell exactly what that material is made up of. Is it made up of a single element or two elements or more than two elements, depending on the spectra that are showing now. In the case of the absorption spectrum, is a lack of spectral lines. In the case of the emission, it's only and only those lines that are showing. So that's the difference between the two, the emission spectrum and the absorption spectrum. Both of them are useful. Both of them are very important. For the case of the sun, for example, radiation is coming in all frequencies leaving the sun. All frequencies are leaving the sun. But the minute they hit the atmosphere of the sun, hydrogen is in abundance there. It's going to absorb its frequencies, at least in the visible. Obviously, it's not just the visible that we're concerned with. There is the ultraviolet and the infrared. Or if there's another element like helium, for example, it's going to have its own absorption spectrum. So when I look at the spectrum of the sun, I see everything but some lines are missing for the most part. That's exactly what happened. So when they first analyzed the sun, they saw, okay, I have these lines correspond to hydrogen. I know hydrogen is on the surface of the sun and it's in abundance because it's very intense, these lines are. But then there is this element. They didn't understand what it was, so they called it the gas of the sun, helium. Remember, helio stands for the sun, because they believe that that gas is unique to the sun. It turns out that it exists actually on Earth, and that is the second most abundant element in the universe after hydrogen. So that is the power of these things and how useful it is for us. Okay. So again, we just finished the units dealing with the solar system. I know some of you were wondering what happened to Mercury and what happened to Mars, actually, what happened to the other two planets, Uranus and Neptune. Well, we already sampled enough that hopefully you guys can read those on your own. And they're interesting topics by themselves. I mean, there's a lot of things you could say about in every one of those objects. Uranus in particular, for example, because it's spinning on its side, which is kind of weird compared to all of the planets either sitting on their, basically standing on their feet and spinning, except Venus, we saw it's spinning on its head. And now the other one, it's on its side, Uranus. So there's all kinds of discussions in here. Neptune and how it was discovered, which is really a big story in here that we didn't really have time to go through. But it was Uranus was discovered by Herschel. And then Neptune was discovered by two mathematicians, completely not observing anything, one in France and one in England. And at the end, or was it USA or England? I forgot that. Anyway, the point in here is that math helped us find Neptune. And then from there, we have those 8 planets and the beautiful stories to go with them. We had a chance to go through the moons. We talked about Triton, Titan, Europa, and all of the other things, which are interesting topics. So I think we covered enough materials for the solar system so that you can go on your own. It's not a complete story. Yesterday where was it? Yesterday or the other day? Basically, there was an article about the missions that are coming in 2024 for in about 2 years from today by ESA, the European Space Agency, toward the moon Europa. Europa is the 4th moon of the smallest moon of the big moons of Jupiter. But now there is all kinds of interest, renewed interest to it, and there is a mission dedicated to it, just to go and see if we can find us, collect basically because there is eruptions from underneath the surface from the water that evaporates. So now they're trying to send a mission to go and collect the water that is coming from the surface of the planet as it's being ejected from underneath, and try to find organic matter or organic life in it. Okay. That's really the whole thing, and it's a big deal. That's in 2024. So there are all kinds of topics of interest to us in the solar system. Unfortunately, that's all the time we have for the solar system. So we're going to move on, and actually we moved on with Unit 21, and we're preparing ourselves to get to the sun. And you will see that it's a fascinating topic by itself. It involves all kinds of knowledge that we need to explore, basically nuclear forces, both the weak nuclear forces, the strong nuclear forces, electromagnetic forces, and also gravitational forces, which are all the forces of nature combined. And then we're going to take that knowledge and later on try to understand the stars themselves and try to classify them and move on beyond that topic. Okay, there's a lot of materials to cover, so hopefully you guys are excited, and we'll cover them in time. Sounds good? Okay, so for those sitting in astronomy, I will see you guys at the lab, I should say. I'll see you guys in about a couple of hours. The others, I will see you guys next week. Thank you.